Hi, everyone, and welcome to part two. We are going to pick up right where we left off, and we are starting with a second regression model. Now we're going to use that second dependent variable, y2. So I'm just going to call this lm2, keeping things simple. We're going to walk through the steps that we just did with our previous model. So we look at it, and initially seems fine, but let's check assumptions visually first. Again, not looking good. Also not looking good. So based on visual inspection, not off to a great start with this one. So it looks like residuals don't appear to be normal. And visually, it also looks like we're going to have heteroskedasticity as well. Yeah, so kurtosis 13. Yeah, not surprisingly, statistically significant. So non-normal residuals. And then both the tests for heteroskedasticity, also significant. So we have non-normal residuals and heteroskedasticity. So let's work through the process we did again. I'm going to use that Stargazer package again so we can compare. But similar commands, just putting in lm2 now. So let's have a look. Again, coefficients are going to stay the same. But similar idea here. We see the robust standard errors, so much larger than they were, or much larger than the original standard errors for sure. Again, similar to the last scenario, the conclusions would fundamentally be the same in this case. But again, that's not always going to be the case. And notably, I believe I mentioned this earlier, using a heteroskedastic corrected covariance matrix doesn't address the non-normality of residuals technically, but I noted the non-normal residuals generally less of a problem compared to something like heteroskedasticity, especially if you have a good sample size. But I'll talk about in a second how you could use an approach like bootstrapping and address both those assumptions. But first, before I get into that, I want to talk about how you would implement this if you were using maximum likelihood estimation. We use maximum likelihood estimation when we talked about path models and mediation, but you could use it for a linear, just kind of a normal linear regression model as well. Again, you could use either one. So I just want to show you how you would do that, how we could approach it. And again, I'm using the Levon package, which is one of my go-to packages. Remember from last time, you'll see we're specifying our model first, and then we actually fit it. Again, you can name it whatever you want. Just naming it model 2 because it's our second model with the dependent variable. Very similar command. You'll see we're specifying SEM, even though this is just a regression model estimated with maximum likelihood estimation. So there you'll see we have the maximum likelihood. And these results roughly the same as when we used ordinary least squares estimation and did not use a robust approach. So to get a robust approach, we are going to specify this estimator as MLR. And I will talk about that in a second. But for now, really all you need to know is that's how we would actually get the robust or sandwich standard errors if you're using maximum likelihood estimation and using Levon. The MLR estimator isn't the only one that you could use here, but the reason I mentioned it is not only can we use it to address violations or departures from multivariate normality, but it also can be used in the presence of missing data, which is what we're going to be talking about in the next set of videos. So in terms of, I ended kind of the last video talking about how a robust kind of approach can become a good almost default routine to use. And this is a perfect example of that. The MLR estimator, just literally, 3 letters, adding a little bit of code in there. Not only can we get robust standard errors, we can also address missing data, or at least certain types of missing data, pretty well. So there's some small points about it when you're doing model fit tests. I have some additional information about that as we go on. I'll just briefly talk about a couple things, and then I want to talk about bootstrapping at the end. It does get a little bit advanced, though, so maybe this won't be interesting to all of you. First, I'll note the first way I actually learned how to address something like a non-normal residuals or something like that, I always learned a look at the univariate distributions, and then if they're not normal, we do some sort of transformation to them, is how I originally learned. And you'll still see this every once in a while, but generally I would encourage you to avoid doing this, mainly for the broad reason is I think it's kind of the least elegant or the most inelegant approach. And one basic drawback can be the interpretation. For example, if you do a log transformation of your dependent variable or something, it gets a little bit weird to try to interpret that. And in many ways, we'll be talking about a lot of different models going forward. So if your data has certain characteristics, usually there's going to be a model that's appropriate when the data has those characteristics. And I think it's always generally better to use the model that's appropriate given your data, rather than trying to change your data around so that you can use a particular model. So just want to briefly know that. That's why I didn't talk about that at all, because I think it's broadly just kind of an outdated and unnecessary strategy that really doesn't have any advantages to it. I also have a brief point, not super brief, a little bit of a discussion talking about kind of sample size issues, and talking about that a little bit more. But what I really want to get to is talking about using bootstrapping. So we talked about bootstrapping when we talked about testing mediation or testing in indirect effect, but you can use bootstrapping for other things as well. One use is even with small samples. That's why I mentioned sometimes it can be used with a small sample, even something with a sample size of like 20. There's some evidence, at least, that you can still get pretty good parameters with something like that. There's a lot of different ways you can implement it. I showed one that's really easy, and I'll kind of show that kind of at the end. But first, I want to show kind of the more difficult way and talk about kind of bootstrapping more generally. So here I'm actually going to create one to do it for me. So the first thing I just did here is I just created some empty shells. But like bootstrapping, or we're talking about bootstrapping when mediation, we talked about the idea of we're empirically generating a sampling distribution to use. So that's basically what we're going to be working through right here. So our two coefficients, the x1 and x2, we want to empirically generate a sampling distribution for those. This next part of what I'm going to do is called a loop. First thing I'm going to do is set this seed. You'll have to do that if you want your results to be the same as mine. It's just so you have to reproduce it. A part of bootstrapping and some other kind of resampling techniques, but bootstrapping in particular, we resample our own data. And in this case, then we estimate our model, we save those coefficients, and then I'm going to do that 1,000 times, specifically in this case. You might remember before, generally you want to do at least 5,000, if not something like 10,000, but to keep it relatively straightforward, I'm going to do 1,000. And to walk through this again a little bit more, so this is the line where I'm actually resampling the data. So basically what we're going to do is you can think about the whole data set. You grab, randomly select one case, put it into a new data set up to a sample size of 500, because that's our sample size here. So that's what I'm specifying here. Basically, we want a sample size of 500, and I want you to randomly draw data from our own data set. And the replacement is true means that we can still technically grab the same case, or the same case could be randomly sampled multiple times. So we randomly sample, get a bootstrap sample. You'll see the estimate the model. Then I'm saving these coefficients. You see the money sign there. Again, using this object-oriented language idea, I'm specifying specific coefficients there. Now I can run this. It goes pretty quick with just 1,000, though again, it might depend on your computer. You can always play around with that a little bit. Nothing really popped up so far, right? You'll see just some blue, but you'll see we get some values down here. So now let's do some comparisons. So that was the original model one up here. And then, oops. The next one is with the robust standard errors, so the slightly larger standard errors. Now that we have that distribution, we can look at something like the mean, but in this case, we're focused on standard errors. So we can use the standard deviation. So again, we did that 1,000 times randomly resampling our own data, estimating the model, saving those coefficients. So we did 1,000 of those coefficients. So now we have a distribution, and we could do something like take the standard deviation of that distribution and use it as the standard error. So you'll see here 0.067, which with rounding would be the same as when we use the sandwich estimator approach. And illustrating the same thing with x2, again with rounding, it would round to exactly the same thing. So just wanted to point out, again, you wouldn't have to actually write all this code yourself, though if you're nerdy, I think it can actually get really fun to play around with that a lot. And you can do things like I'll show here. You can look at the distribution. So this is the distribution of that coefficient x. And we can actually check out that distribution. So for example, is it normally distributed? Generally, you'll note with the mediation, we talked about the product of coefficients, that distribution is not normal. Bootstrapping here, you could use it, or it's often referred to as a non-parametric technique. And we could use it in that way, where we're not making any assumptions about the sampling distribution. So again, we're generating it. And what we could do here, or one common thing, is to create, just like we did with indirect effects, we could basically do percentile-based bootstrap confidence intervals. So here, if I wanted to do that, right, maybe rather than something, standard deviation could be fine because we looked at it and it looked like a normal distribution, but we could also just not make any assumption about it and just use the percentiles to get something like a 95% confidence interval. So there's lots of fun things you can do to play around. I might bring that up more. And if you are interested, I'd be happy to do more videos on it. But real quickly, I'll show you this is a lot easier to implement in Lavaan if you wanted to implement that bootstrapping. So see here, this is 1,000. I didn't specify 1,000. The default is 1,000. So no, if you want more than that, you have to specify it. So here it's just running again. It took a second. We saw that stop sign. Oh, I already wrote that. So here, right, standard errors is letting us know, yep, they're bootstrapped, and then we get them right here. You get that summary. So relatively simple to just do it in something like on rather than kind of writing out your own code. But it can be cool and give you lots of flexibility if you get your head around coding these types of approaches, whether it be bootstrapping, but towards the kind of very end of the series, I'll be talking about more sample size planning, and we'll use a different type of resampling approach, but it's a similar idea where we're repeatedly doing something and then basically representing a distribution in some way and then using it in some way. So here you get the names are a little bit off. They might show up as V's on yours depending on your version of R, how they pop up, but just so you can actually see that if it doesn't show you the Y2 and X1. Very last thing I want to point out, and I'll be talking a little bit more, but we talked about likelihood ratio tests or doing a chi-square difference test before when we talked about, for example, testing and comparing two nested models. So you can still do this type of approach using a robust estimation routine. So say you had a path model and you're going to use that MLR estimator, and then you're going to compare it with another one. You do have to make a small correction. It's called a scaled chi-square difference test. Satora Bentler. So you just have to specify that. But I'll be talking about that a little bit more down the line. But thank you for watching this video. I hope that it was helpful and interesting, and I hope to see you in future videos.